Hello, this is a video about the Maclaurin polynomials and in the end also about the Maclaurin series. So I just throw it at you. This is the formula for the nth Maclaurin polynomial. And it's always with respect to a certain function. In our case, we call it f. And what does it do? Actually, each following polynomial approximates the function better and better around the point or the axis x equals 0. All right, so for each next polynomial you compute, you get a better approximation. So, well, let's just quickly look at this formula. What do we find in it? I find these factorials. And it's good to remember maybe that you know, 0 factorial equals 1. And so does 1 factorial. And then 2 factorial equals 1 times 2 is 2. And 3 factorial equals 1 times 2 times 3, which is 6, etc. And what else do we find? We find here these derivatives of the function f, but not as such. We find them with the 0 plugged in. So never the derivative itself will pop up in your Maclaurin polynomial, always with the 0 substituted for x. Where does the x come from in your polynomial? That's from these extra terms, x to the 0, x to the 1, x to the power 2, x to the power 3, x to the power n. That's why we get a polynomial. That's because these x's are here. All right. So this is a complicated thing, and examples will make it much clearer, I suppose. There's just one more notational thing with these f, with the n between brackets there, we mean the nth derivative of f, derivative of f. That's important, because at some point you're going to be tired of putting all these primes. If you want to put 15 primes, that's not fun. You just put a 15 between brackets. So if we want to compute the first polynomial, the first Maclaurin polynomial, we don't need to do much. So let's do the first. What do we need to do? We just need to plug 0 into our function. So we get f of 0 equals, yeah, this is our example, right? It's e to the power 2x. So it will be e to the power minus 2, 0 equals simply 1. And that's all we need to do. So our 0th Maclaurin polynomial, p0 of x, is actually constant polynomial because it's 1 divided by 0 factorial, which is 1, times x to the power 0, which is 1. So the polynomial is the constant polynomial 1. Is that a good approximation? Well, indeed, this function intersects the y-axis in y equals 1, so in the point 0, 1. So all right, if you stay really close to x equals 0, then that might be a reasonable approximation. But we could do better. So let's look at the second. This is very Dutch. I put an e behind the t. That's very Dutch. I'm sorry. You may have heard from my accent already, I'm Dutch. So let's do the second polynomial. What do we need to do? We already have f of 0, so we don't need to worry about that anymore. But I do need f prime, so the derivative of f. So there we go. That must be minus 2 of e to the power minus 2x. Now I can, of course, plug in the 0, and I simply get minus 2. Because e to the power 0 equals 1. So far, so good. So p1 of x, our first Maclaurin polynomial, is just our 0th polynomial, which was 1, plus this term here now. So let's plug it in. We have minus 2 divided by 1 factorial, which equals 1, and there's x to the power 1. So all together we get, let's write it here, 1 minus 2x. Okay, so that's a linear function, and it says that basically, I haven't drawn it very well, it tells me, because it should have slope -2 here. So it should have slope like that. And that's a better approximation, because you can imagine if you get the slope right here, it will stay close to this function for a little bit longer. So let's move on. Yeah, okay. There maybe it was not so nice that I wrote first here, because should actually call this the zeroth polynomial, and this is then the first polynomial. And then what we're going to do now actually is the second polynomial of the polynomial of degree 2. So what we need is the second derivative, which we are going to compute here. It is, of course, we get another factor of -2, so we get 4e to the power -2x. And then we're going to plug in the 0, and we get simply 4. And that means that our second polynomial, a degree 2 polynomial, p2 of x, is going to be everything we already had, which is 1 minus 2x, plus this new term, which is 4 over 2 factorial times x squared, which I can simplify to 1 minus 2x plus 2x squared. Okay, that looks absolutely fine and good. So maybe we do one more and then we try to write down what the general one is. So now the third Maclaurin polynomial, we need the third derivative. So now instead of these 3 primes, just to invite this notation for you, I'm going to write this 3 between brackets, and I need the third derivative of this function, which should be minus 8 times e to the power minus 2x. I plug in 0, so we can do it. I simply get minus 8. And that means my third Maclaurin polynomial will be everything we already had, 1 minus 2x plus 2x squared plus, and we get minus 8 divided by 3 factorial times x to the cube, which is 1 minus 2x plus 2x squared plus 8 over 6 times x to the cube. And maybe instead of rewriting the whole line, I might as well simplify this to 4 over 3. There you go. And on and on and on. Can we say something about this general term? I think we can at least express for the nth polynomial, we can do a little bit of computation. We could say what's the nth derivative of our function? I notice that each time we just get a factor minus 2 in front of it. So actually the derivative is minus 2 to the power n times e. That means that in 0 we get minus 2 to the power n. And indeed, what we would get with our nth polynomial is that the p of x equals everything we already had. So 1 minus 2x plus 2x squared plus 4 over 3x cubed plus, and now the famous dots, until we reach the formula minus 2 to the power n divided by n factorial times x to the power n. So you have some sort of general expression, and you could even write it as a sum, like, and now it's good to show you this notation. What is it actually that you're doing? A more formal notation is that you run an extra variable, k, from 0 up to n, and actually each time what you get is this minus 2 to the power k divided by k factorial times x to the power of k. So that's a more formal way to write it. And if you're not familiar with this notation, you'll probably be a little bit overwhelmed. But if you are familiar with it, you find, oh, that's beautiful and short. So I wish you the second experience maybe, but maybe the first one's not bad either. So this is the Maclaurin polynomial. And the series is what you get if in this situation you think of running n to infinity. And so basically you put the dots behind this and you imagine what follows. And each time, of course, that you add an extra term, your approximation of the function gets better. And you can imagine that in the limit of these infinitely many terms, your approximation would be perfect. And actually, it's not the case for every function. Not even every function is so many times differentiable. But there are some series that are infinitely many times differentiable. And indeed, this approximation is beautiful. And those are so-called functions that are analytic at zero. But OK, that's just a side remark. I think for now, what I wanted to do is just show you how to compute your Maclaurin polynomial in a concrete case. And I hope that helps you with many more beautiful computations of Maclaurin polynomials. So good luck and goodbye.